I'm Charlie Sullivan. I'll be co-chairing this session with Rob Wills, who's the CTO of Citizenre Corporation, a solar PV startup. And I think it's clear that, especially from the end of the last panel, that science and technology are a very important part of addressing energy problems. What may not be clear is the breadth of different technical topics that are essential. And in this panel, we tried to pack in as many experts as we could. We can't really begin to cover the breadth of important topics, but we have a sampling that gives you an idea of that breadth, and we have people who are all real leaders in their respective areas. And we will begin with Sean Casten, who is the president and CEO of Recycled Energy Development, which is a company that he just founded this year with his father, Tom, which is aiming to profitably reduce greenhouse gas emissions by recycling industrial waste into high-value heat and power. And I should also point out that although that's a new company projecting to do great things, he has a very solid record of doing the kinds of things that he's talking about doing in the past, and has strong credibility there that this is not just an idea but something that can actually be done. And I will turn it over to him.
Thank you, Charlie, and thanks for the flattery. We're in the midst of a fundraise, and I may ask you to come and talk about my credibility at some point in the not too distant future. I want to talk about the very broad concept of energy recycling. It's what our company does, and one of my favorite energy policy theorists is David Lee Roth, because he had this line after he'd trashed a hotel room with Van Halen and there were a bunch of scantily clad women running around, and he got chewed out for taking advantage of his position, and he said, I don't act this way because I'm in rock and roll. I'm in rock and roll because I am this way. The reason I make the comment is because the reason that we got into this space of energy recycling is not because we think this is the sexiest technology and the technology to push, or even really that it is a technology, but because if you start from the macro position of saying we want to reduce as much greenhouse gas as we possibly can, and we want to do it while making as much money as we possibly can, there's frankly not much else that even comes close. I think you can probably broadly say that end-use efficiency is probably about the best on both metrics, and this is a close second. Total market opportunity for this stuff. Presently in the United States, there's 84 gigawatts of combined heat and power. These are plants that are all at least twice as efficient as the U.S. power grid. Coincidentally, look a lot more like the first power plant Thomas Edison built than they do like a present power plant. To put that in perspective, we presently have about 100 gigawatts of nuclear capacity in this country, which makes something like 10% of our power. So this is one of the really important parts of our power grid that no one talks about. The potential for additional combined heat and power, the DOE has an estimate of 135 gigawatts. I think that's really small. I think the actual number is bigger. We haven't done the analysis yet to figure out how much bigger it is, but the reason that I say I think it's bigger is that the most market analyses assume that thermodynamic laws are fixed, which I agree with. They also assume that regulatory laws are fixed, which I disagree with. And there's a lot of constraints in that analysis that assume that we're always prone to have dumb laws. And I don't think we need to be quite so limiting. But at the very least, that's a big number, even at 135, and I think it's much bigger. The potential for waste energy recovery, which is really just a subset, but this is looking at industrials where you can go in, find waste heat, and profitably convert it to power. Emphasis on profitably, because we'll get to how that number is actually much bigger, is 40 gigawatts. These are huge numbers. An average coal plant's about a half a gigawatt. So, the talk from the last time about, are there options better than coal? Without question. I mean, you deploy all this stuff, we don't need any coal. You just at least on new coal, you knock it out of the picture. So we've got this total potential that is in excess of 10% of our peak power load in this country, probably closer to 40% of the megawatt hours, because an awful lot of the generation we have doesn't run very often. Whereas this stuff, because it's so energy efficient, you never really have an incentive to turn it off, and so it tends to run 24/7. You'd replace 300 coal plants and massively reduce energy costs and greenhouse gas emissions. I think it's helpful to see a scale of what this is. This is a project that was built by one of our predecessor companies. If you look, that's Lake Michigan there, and the buildings in the skyline are Chicago. This is at Koch Energy. It's a U.S. steel plant in northern Indiana. Generally not a nice place. Booking made the comment that energy efficiency isn't very sexy. This is not sexy, but it's really important. The scale here, these are trucks. This is an enormous scale. Along the back here, these are 268 coke ovens. If you want steel, you need coke. Coke basically takes coal and cooks everything out but the carbon, and you're left with gas off the top. All of the gas from these coke ovens at this plant before this facility went in, and indeed at all of the neighboring plants in northern Indiana, goes to a flare and gets burned in compliance with EPA regulations. What was done here was to say, let's pick up, and you can't quite see the piping, but essentially all the pipe comes over. This right here is the powerhouse. Makes 95 megawatts of electricity. A portion of the exhaust steam goes on to provide steam at the facility. A portion of it goes into these cooling towers. And, sorry, the mouse is moving too fast. These are the bag houses and the pollution control equipment on the back end. This project was built and makes money at 2 cents a kilowatt hour. After the investor gets their 2 cents a kilowatt hour and gets a pretty nice return on their initial capital, U.S. Steel saves $40 million a year on their energy costs by virtue of having this facility. And in 2004, the total power output of this plant exceeded the total power output from all of the world's grid-connected solar power. This is, and I'm not raising that to say that we've got to pick winners. We need every technology that's out there. But it's important to understand the scale of what this stuff is. This is a single plant. There's 3 other plants right next to it on the river that haven't done this. So what are the technical challenges? I'm on the business panel, and we'll talk about the business panel's issues this afternoon. But there's some pretty significant engineering challenges on this that are fun things for engineering students to think about. The first is that I guarantee that 40 gigawatts number is way low. And the reason is that I was talking with Bill McKibben recently, and he was asking why people didn't do more of this. And I said to him, Bill, how much urine did you make yesterday, and what was the chemical composition? And if I could convince you to drink more or less of a certain fluid to make it stronger or weaker, would you? And have you done that in the past? You know, of course you don't. But you sit there and you say you've got these facilities where this was always a waste product. In some cases, because of the perversity of EPA rules, they've been incentivized to get rid of it as inefficiently as possible. And so you go in and look at a stack where there's, you might have maybe 500-degree exhaust gas, which is kind of the low end of what you can do something technically with. And then you start looking in and saying, well, you're blowing excess air through. Your fan motors are inefficient. You've basically overcompensated on safety and reliability at the expense of exhaust temperature because you didn't care about exhaust temperature. But you can drive all those things up, and as an example, we're doing a project at a silicon factory now that's exhausting at 500, and we think when we're done we're going to get it up to 1200 without changing anything, just tightening up parts of their processes that they never had an incentive to tighten up. So that's an engineering challenge. Really tight integration with the host facility and the power island. We refer to what we do as outsourcing someone's kidney, not to keep staying on the urine jokes, but that's literally what it is. You've got stuff where you're tied into the way in which they generate waste heat, which is the way that they make their process, the way in which they use thermal energy and electrical energy. And there's just a lot of very tight engineering issues, not the least of which is on the pollution control side. If you cool gas so much that your SCR doesn't work on the back end, then you can't get the NOx out and compliant SCR, selective catalytic reduction. So none of these issues are impossible, but they're engineering challenges.